Ilango Ganga. He's talking about a day in the life of a packet. He's principal engineer in Network Platform Group's architecture team at Intel. I'll leave him to do the rest.
Are you able to hear me? Yes. Okay, so I'm going to talk about the platform transformation. So how I'm going to do that is to walk you through the day in the life of a packet in a typical platform when you are running a certain network function, and then I'll explain how the platform needs to transform to perform the complex network functions. So myself and Brian Scurry put together this presentation together. So I'll be doing the talk, but a lot of this content was co-developed by both of us, and of course other team members from Intel as well. So I'll give an introduction of the network function virtualization, but the whole talk is not focused on that. I'll just give a quick recap because most of you know about NFV and SDN, and I will talk about the day in the life of the packet. And as part of the the NFV, I will also talk about what are the three important pillars in NFV and how that translates into building those capabilities into the platform, server platform itself. And I'll also touch upon the ideal end state, where we would like to see this. So Brian Scurry happens to be a good photographer as well, and so these are the pictures that I'll be showing some pictures in between that matches the theme of the talk. And so I'm going to talk about the three pillars. So before that, some of the examples of the applications that takes advantage of the NFV is, the NFV, it happens in multiple different market segments. You can apply these concepts to multiple different market segments. One of them is, cloud, enterprise, comms, service provider. The examples when you take the enterprise side is, virtual CPE, virtual router, virtual load balancer, virtual firewall, and whatnot. And when it comes to the service providers, we are talking about, virtual EPC or virtual provider edge router, and also you can look at, virtual RAN and so on, right? So let's move on to talk about the original goals of the NFV. So why we are here and what we wanted to do with network function virtualization is to eliminate some of the complexities involved in bringing the services, right? So previously it was all fixed function boxes, and how can we untether that and then be able to deploy that in a commercial off-the-shelf server, thereby reducing the complexity and the cost, and also to provide agility. So we want to bring up the services anytime, anywhere, on demand, right? And at the same time, to be able to manage this, if you want to bring up a service, you should be able to bring up and provision the service in minutes rather than days or weeks, like that, right? So the operational cost as well. And at the same time, when we are bringing this capability into general purpose servers, you wanted to have well-defined interfaces so that multiple vendors can bring in their services and interoperate with each other. So you can have a hardware platform, the general purpose platform, at the same time have the VNFs or the network functions be able to interoperate in such a platform. I'll revisit this at the end to figure out where we are, and now let's talk about what are the three key pillars. One of them is the packet processing. In order to bring these services, we need to have efficient packet processing mechanism in the platform. That's the key part that I will be covering today, and the other part is the security. It's also very important to provide the services in a secure manner. So you might be having a data center where you have multiple different tenants sitting in the same data center. You want to make sure that the services are brought in a secure manner. At the same time, you want to make sure that one of the services does not take over the resources of the other service and so on, right? Because these services can be co-located in the data center. So that's an important part. The service assurance is a very important part because when you're having a physical infrastructure, you know how you get the right SLAs, right? So when you come to a commercial server platform and you are deploying these services in a scale-out manner, you want to make sure that we bring in the same level of service level when you are deploying it in a scale-out model. So we'll talk about that a little bit. So in case of a non-service assured platform, right, you are not sure, like let's say if you wanted to have a certain bandwidth or you wanted to make sure that you have certain guarantees, let's say if you want to get some packet performance or throughput, how do you ensure that you get that, right? So the platform, where you are deploying the services, the management needs to be aware of, what kind of service I'm going to get in this platform so that I can go and deploy the service in here. And also when you deploy the service in there, it's not only good enough to say that, okay, I now deployed this particular service in this platform, and the platform has certain capabilities. So I expect that this kind of quality of service metrics can be reached when I deploy this in this platform. But at the same time, I would like to know when the service is deployed, when the service is in progress. You should have the capability to monitor that. When I say monitoring, it could be I wanted to know, on the virtual interfaces, like what's the type of packet processing that I'm getting from this platform, right? Can I be able to monitor the CPU utilization? Can I monitor the the memory metrics? Can I monitor the traffic that's going on a certain virtual network, and so on. So those are the kind of capabilities that we need to have, and in case if there are any anomalies, so that for example, in a certain threshold is exceeding, then you should be able to take corrective action. And that's when we call this, it's a service assured platform. And if you get into, OPNFV, there's a project called Barometer, which talks about, which goes into the details of it, of this, how do we get the service assurance. So I'm not going to cover the details of all this, in this talk, because of my talk, I wanted to go and focus on the packet processing part of it. But still, I want to introduce you to the concepts and where you can go and find information regarding this thing. The other thing is in the security, right? So when you are deploying the services in the data center, historically, the perimeter it's a hardened perimeter, right? So the perimeter is secure, but when you come inside the data center, it's much more softer, right? So it's possible that you have a multi-tenant data center. There are multiple different tenants are co-located in the data center, and it's possible that there could be threats within the data center. So securing the perimeter alone is not good enough. So the east-west traffic within the data center needs to be protected, as well as the services that are deployed on the server platforms needs to be protected as well. So I'll touch upon that a little bit. So there could be attacks in the system. So we want to make sure that you are deploying the services in the right system. So one of the examples is platform attestation. You want to make sure that not only the platform is attested, but also the VNF or the service that you're deploying in the platform is the right service that you are deploying here, right? And the other thing is the data protection, right? So within the data center, you want to make sure that the data is protected. And the data is protected when it is at rest, when you are storing it. At the same time, the data should be protected during the transit. What I mean by that, in a multi-tenant data center, when the data is traversing not only north-south, we know that in a north-south we have gateways or VPN kind of gateways to ensure that the traffic traversing on the internet is protected. We need to have similar mechanisms within the data center where the data is protected. And also you need to have, more finer granular controls in such a way that, certain service of a tenant, when it is co-located in the data center and running in the same server, the resources are protected as well. So you don't want one of the tenants taking away the resources of the other tenants and so on. At the same time, the traffic or whatever the services that you are guaranteeing to a certain tenant, you want to make sure that that is provided to that tenant. And that includes, finer granularity, like, the quality of service metrics, the access control policies and so on. That needs to be now not only at the system level, but it needs to be assigned at the logical level, It could be logical interface level, logical switch level, logical router level, and so on. Now, let me walk through the day in the life of the packet. So in order to do that, let me go through, well, I'll start with a basic network appliance. This is the standard network appliance. I'm not talking about virtualization or anything in here. This is kind of like a vertical box in the sense like uses standard general purpose x86 platform, but it is purpose built for a certain application. So the applications could be like, provider edge router or EPC or VPN. So this is the VPN box, and how you build that, it could have a standard network interface controllers or NIC cards. Depending upon the fan out, you have multiple of them in this system, and then it has a standard processor. If it is a if it is a VPN kind of appliance, then or it's possible that a firewall appliance, but it also needs to handle crypto capabilities. You might have accelerator devices that is also plugged into the same system, and it could be a standard accelerator, PCI Express card based accelerator, or it could be a board that is built in with some purpose-built accelerators in there in order to accelerate your packet processing. And of course, on top of it, you will have a software-based acceleration as well. And a DPTK is an example I'm using as a model, which will be used for accelerating the software in this the application as well. And in this model, as you can see, I'll go through this. I'll show the same picture in a different view, where when the packet traverses through the system, what happens? Like you have a standard network interface controller. As the packet flows from the left to right, you are seeing simple functions like packet parsing, and then you might have a filtering function like looking at the MAC VLANs to make sure that the packet is arriving at the right system. If not, you filter this out. But the key point of this one is to perform some of these stateless offloads, like checksum offloads, and distributing RSS, like distributing the traffic to multiple cores, so that the applications can be processing these efficiently in a multi-core system. But once you get to the CPU subsystem, a lot of the complex functionalities are executed in the CPU subsystem. Here you have a second level, a parser, which goes much deeper into the packet because you are supposed to classify the packets. Maybe you are performing a routing functionality, so you are doing a longest prefix match and so on. Right? You might also have other, traffic management, complex traffic management capabilities and QoS capabilities that are implemented in this platform. And the applications like firewall or IDS, IPS, and those kind of applications are running this platform. And at the same time, I was talking about, crypto acceleration example I'm showing in here. So it's a look-aside model where the packet requires some of the crypto acceleration capability. That could be for, transport, because you want to secure the transport and you wanted to use it for that purpose. Or it also could be an application level, like a TLS or SSL kind of an acceleration, right? That's also possible. So let's look at the, I'm introducing the concept of network virtualization. So some of you might be aware of this concept, but I will draw parallels to server virtualization, which is well known. So in server virtualization, you are able to abstract the underlying physical hardware and hardware resources like the CPU, memory, storage, and so on. And we can pull these resources and be able to create, virtual machines, and you can assign logical slices of these resources to each one of these virtual machines so that these can run workloads independently on these virtual machines. Similarly, in the concept of network virtualization, you can abstract the underlying physical network and be able to create logical networks on top of that. And within the logical network, you should be able to assign physical logical resources like virtual switches, virtual routers, firewall, load balancers, and whatnot. So this is a concept that's used in a typical multi-tenant data center. So where you wanted to be able to, multiple tenants wanted to go into the data center and wanted to bring in their own virtual machines, but not only they bring in their own virtual machines, but they want to interconnect those virtual machines within the virtual network with the policies that they dictate, right? So that's the model that we are talking about here. And typically the network virtualization technology that's enabled by means of overlay networks or tunneling. So underlying network is an IP network. It's a standard IP fabric. That's what is you are getting from the physical network. But on the logical network or the virtual network, we create that from the overlay. An example of these technologies is VXLAN, NVGRE, or Geneve. These are the overlay encapsulation. very similar to how we are doing the IPsec VPNs, where we are able to come in from remote offices, homes and locations, but we're able to log in into the corporate data center and be able to get the extension of the corporate network across the public internet. The same thing is happening within the data center, where you're able to create these multiple logical overlays within the same network. And the technology that's used, I talked about the tunneling technology, but the virtual switch today is being used for creating these overlays. Example of the virtual switches, we can talk about any of these standard switches like OVS, or the commercial switches like VMware's virtual switch, or you can talk about Microsoft has their own Hyper-V virtual switch in order to create this. There are of course, other virtual switches are also available for performing this capability. I've also color-coded in here showing, green is the physical network part of it, and then the purple is the overlay network part of it, the logical network part, and then the collective resources that are within the virtual network, right? That's what I'm showing it in blue. Just keep that in mind when I move to the next slide, where I'm going to show a packet flow diagram here. So the same diagram that I showed in 2 slides before about how the packet traverses through a virtual appliance. In the network virtualized model, you see the same network controller now has to deal with different levels in the packet, right? In the bottom of the slide, I'm showing you the packet format, where you are seeing the outer header, which is shown in the green. That's dealt in the physical network. So the physical switches or the IP fabric is forwarding the packet based on the outer header, but the inner payload, the purple one, belongs to the logical network. So same way, when it comes to the platform, we are talking about the platform previously, which was a simpler platform. Now the platform needs to handle not only the outer headers, but it also needs to process needs to understand that there is a tunneling happening here, right? You have an overlay network here, so you're able to process the overlay header. In case of a VXLAN, for example, you're having a VXLAN header in here, which I'm showing in here, and there is a virtual network identifier as part of the VXLAN header that gives you kind of a logical namespace that enables you to identify a virtual network. And you should be able to process that in there. And in case, if you are handling that, terminating those tunnels in the hardware, then in that case, the hardware should be aware of those tunnels and be able to terminate those tunnels. In some cases, you may not want to do that because you wanted to have that capability done in the virtual switch like before, but the hardware happens to be provides an acceleration capability. In that case, the hardware is aware of the tunnels. It understands the logical network. It understands where to forward the traffic into the platform, but the actual, functionality, the termination functionality, is performed in the virtual switch in the software. So the software is much more agile. You may be able to bring in these services at much faster rate, and you might want to handle it in software. And also, you might want to look much deeper inside the packet. So as you go into that, and I'm also showing on the right-hand side where you have these multiple applications, the network services running in the platform, and these services needs to send traffic between these services, which are co-located on the same platform. In which case, the virtual switch is not only sending traffic in and out of the platform, right? But it's also doing traffic, communicating between the network services or the business applications in the same platform. And of course, in such a model, you will also have, I'll bring in the security aspects of it. We talked about security and securing the traffic within the data center, so when you're communicating within the data center or the east-west traffic. So in which case, not only that you are doing the tunneling, but you also are making sure that when the traffic leaves the platform, it is encrypted, it is secure, right? So there's also, I'm showing two blocks in here, which shows the encryption and decryption in the hardware level. That's the inline encryption and decryption. So where you are bringing in the traffic, but at the same time, it is secure. You're having a secure transport when it is leaving the system. It's also possible that at the application level, you have, TLS or SSL kind of an acceleration, and you wanted to have those capabilities as well in the platform. So you might have multiple levels. I'm not saying that you need to have all of this, but in some cases, you might be running it in, x86 instructions like AES-MI kind of instruction. In some other cases, you might want to use hardware. That depends upon the performance metrics that is required by the application. But this shows an example how a simpler system now becomes much more complex when you are dealing with NFV network virtualization. So moving on, now let's add one more level of complexity by bringing in, services like firewall, load balancer, and so on within the network, within the virtual network. So, a tenant who goes into the public data center or a private cloud kind of an environment creates a logical network, but they also wanted to bring in their own physical equivalent of the appliance, like firewall. If you wanted to go from your enterprise to a public cloud where you have a logical network or a virtual network created in there, you might want to do a VPN into your own virtual private network. And then once you are into that, then you also wanted to have policies like firewall policies applied, or you might want to do IDS, IPS, like similar to how you would have done in a typical enterprise kind of a data center. The same thing you would like to get in a public data center as well. And so when you are doing that, you are going through multiple different services before getting into the workloads. Right? So there's a business application that's running in there, but before you reach the business applications, you're talking about going through a VPN service or a firewall service or a load balancer before you can reach the business application. And the process of doing that one is service chaining. And when you have multiple different logical entities co-located in the same physical server, or it could be separated in the data center, but you will have a logical equivalent of that. So you need to do the chaining across these multiple different services within the virtual network. So not only you are doing an overlay, but within the overlay, you're also creating a way to chain the services together. So of course, you need to be able to carry metadata between these services. I'll talk about that in the next slide. So I'm adding one more layer. Basically, it's a service overlay. So on top of the network virtualization, we are talking about a service overlay. So within the service overlay, you will have multiple different services. Like it's possible that you have, certain traffic which came in here. You went through a service classifier, which is an example, the terminology that's used in service chaining. The service classifier might decide that, okay, for this particular type of traffic, I need to hit, a firewall or IDS service before it gets to an application. Whereas in another case, I might follow a different kind of, service graph before I reach the service. So you will have multiple different service paths that can be orchestrated at the service orchestrator can go and create these services. And this happens within each one of these overlays. It's possible that I have a virtual network 1 that has a service A, service B, and service C chained together. And similarly, I will have a virtual network, B. Within that, I might have another service A, B, and C chained together. And so the service plane that provides this isolation between logical network A and a logical network. Now let's look at the same, service chaining. Now I'm trying to draw that on a platform when the packet traverses from east to west. What happens? So the same, network interface which I showed earlier now has to deal with one more level of complexity. If you look at the bottom, I'm showing the packet format where we have an outer Ethernet header. In some cases, it could be encrypted, right? More and more, there are some deployments that are not having encryption, but all the newer public cloud kind of an environment, you can see that, it's more and more encrypted. And then behind that, you have, the service. If you have a service overlay, we are also talking about network services header. The example of this one is NSH. That is an example. You could use other protocols as well, but now, people who are following the ETF might know that NSH is developed in the service chaining working group, and that's an example I'm going to use here. And what this allows is to carry the metadata. So it's possible that you do your service classification and then figure out that, okay, this service needs to take a certain path, and then you wanted to carry that metadata in there. And that's what is coming in the network services header. So now in the network interface side, not only that, you are dealing with the tunnel processing, but you also are dealing with service headers as well. And be able to interpret the service header, and based on that, you may want to forward the traffic to the appropriate service that's running in the same box. So in this box, I'm trying to show multiple different services. Example of them is a gateway router, and then there's a VPN service, and then a firewall service, and IDS, IPS service I'm showing in here. And this example, I'm also showing that the traffic is flowing between these services nicely, but this is the possible combination. There could be multiple different combinations where you don't have to go through all these services. At the same time, it need not be running in the same box. It's possible that these services could be distributed across in a scale-out model in the data center, in which case you might want it to go out of the box and then come back in. But the key point here is now the platform needs to evolve to handle these complex scenarios. It's no more a simple packet processing, but it needs to understand and deal with multiple different capabilities that we are talking about. So on top of it now, you still need to perform the other functionality. I talked about the checksum offload and stateless offloads that are typically offered by the network controller. That needs to be handled here. And now it's a lot more complex because now you're distributing the traffic by peeling through the various layers in the packet, and then forwarding it to the appropriate application. The application still needs to perform those other complex functions. So once it comes to the CPU subsystem, we are talking about the virtual switch that deals with if the services are communicating among each other within the same platform, we are talking about virtual machine to virtual machine switching as well that happens within the platform. So it also creates a multiplicative effect. So if, let's say, for example, a 10 gig traffic coming into the platform, if you are creating an internal service chain that needs to do, let's say, 2 or 3 hops within the same platform, we are talking about the 10 gig getting magnified to 20, 30 gig and so on. So the internal the fabric within the platform, whether it's happening in the software or whether it's happening in hardware, now needs to be able to handle 3x amount of bandwidth, not only X amount of bandwidth, which if it happens from the east to west, but within east-west traffic within the same platform now needs to also be handled within the same virtual switch. So the packet processing capability, if it is running in the software, we're talking about the packet processing capability of the vSwitch needs to also handle the inter-VM traffic or the VNF traffic as well. So let's look at the future NFV platform. So the future NFV platform needs to be able to handle higher throughput. First of all, coming in from the network, of course, the network interfaces needs to be capable of handling this throughput. We are talking about 2 gigabit, 10 gigabit, and then going forward, we are talking about 25, 50, 100, and so on, right? So that's basically what I'm talking about. Depending upon the platform that you are building, or depending upon the throughput you need in terms of I/O, you would still have a mix of different kind of interfaces. But in a large public cloud data center, you might see a homogeneous, some level of homogeneity where most of the interfaces are pretty much uniform, like you have a 10 gig or 25 gig or so. And of course, the platform needs to handle, as I mentioned, network virtualization, tunnel header processing. It's not just a single tunnel header, because you can see that there's a preference, like depending on which service provider you're going into, they might be able to handle different kind of tunneling capability. So depending on the service provider, you might want to handle different kind of secure transport capability, because you want to encrypt the traffic when it is in motion within the data center. And then also, as I mentioned, about ability to handle the network service header processing. And of course, virtual switching as well. So if you wanted to perform virtual switching, as I mentioned, we wanted to handle the virtual switching efficiently in software, or in cases you might want to provide some acceleration from the hardware. And at the same time, if you're having the VNFs running in the platform, you need to have an efficient or way of transferring the data between these physical interfaces and the virtual interfaces. Or in case of, if you're running a virtual switch, in cases you also wanted to have the logical or virtual interfaces that are standardized in a much more consistent and standardized manner, so that you can bring in multiple different VNFs from different vendors and be able to operate on this platform. But if the VNF want to take advantage of some of the acceleration capabilities, like it wants to crypto acceleration capabilities, or if you wanted to get packet processing acceleration capabilities, then you need to have APIs in order for the VNFs to take advantage of those capabilities. And of course, in order to provide good service assurance, we are talking about monitoring capability, right? How do you ensure that the proper QoS capabilities are provided by the platform, and at the same time, telemetry. You want to be able to monitor the various different metrics in the platform. One of them can be happening in the logical interface or the virtual interfaces. Or we're talking about if you have a vSwitch, what are the various switching counters that we are talking about, and then if you are how do we how do the platform resources like the memory resources, the CPU, other cache utilization, all those kind of metrics that can be collected from the platform, temperature monitoring, power monitoring, and so on. And so that now the orchestrator has this information, so it can intelligently do the workload placement. That's an example, right? Or if there is a failure happening, it's possible for moving the virtual machines or the virtual network services from one platform to another platform for providing high availability. And of course, we continue to have software optimization. Like example is DPDK. If you're taking a vSwitch and you want to do the acceleration with the vSwitch, we're talking about example of that one is OVS DPDK that provides better packet processing, better packet handling for the virtual switching. VPP is another example, and also at the application level, where the VNFs wanted to have a DPDK in order to accelerate the applications as well. So both can coexist, where you have the network function, NFV infrastructure part of it, where the vSwitch belongs to, is accelerated using DPDK kind of a software acceleration. At the same time, you are also having the VNF acceleration as well. Sure.
Pardon me for my ignorance, but if the frame is copied between two CPU complexes, is it going to go down to the NIC and then back up to the PCI bus, or is it going to get memory copied?
So not necessarily. Both the answers are true, in the sense like in some cases, the customers would wanted to have a better performance, in which case they wanted to send it to the hardware because they might be using the hardware-based or acceleration from the network controller, in which case part of the vSwitch functionality, that data plane functionality might be running it in hardware. So I'm talking about the hardware fastpath, right? In which case the traffic is going down to the NIC because you are kind of a pass-through model. So where your VNF is directly attached to the network controller, and then the packet is going to the NIC and then bounced back into the other virtual network function.
But
right? That's the model where it goes to the hardware. But the other model which I showed you is a vSwitch that's running in software, in which case you are switching between the VMs in the software-based switch. Yeah.
But isn't the fundamental bottleneck in these devices PCIe bus?
That's correct. So that's why both has its own pros and cons. So in one of the models, where the PCI Express will be a bottleneck because you're also handling north-south traffic that is coming in and out of this, the system. At the same time, you also have, a lot of east-west traffic, in which case, if you're also using the same PCI Express bus, that becomes the bottleneck because you're sharing it. So it's a trade-off in the sense like, in some cases, you want your VNF is predominantly, north-south traffic, in which case you wanted to completely pass through and you want to get as fast as possible into the VNF. And in some cases, you're also latency sensitive applications, in which case you wanted to do that. But in other cases, you might wanted to have, software-based vSwitch. It can take advantage of the internal, platform level capabilities to do the VM to VM switching. But of course, it might be bugged by the software bottlenecks in that case. That's what we are trying to alleviate by having the OVS, DPDK as an example. So let's look at the ideal end state where we wanted to be, and I will just do a recap of the previous slide, or the first. I showed you, the NFV goals and where we are here. And the one thing I wanted to show here is the same slide. I'm just trying to show that, what are the important points that we are talking about is we need to be able to have a consistent virtual network interface. This is a challenge today in the NFV, where you wanted to have a VNF that's developed, be able to run across multiple different platforms. So whether the platform, provides hardware acceleration capability or software acceleration capability, or you have a standardized interface that's able to abstract the underlying resources in the platform and be able to run in that environment. So that's where we wanted to be, and so there are some challenges in here, and the industry is evolving there in order to provide a consistent interface in here. That's one important part. The second important aspect is now the platform would have multiple different capabilities. We talked about hardware and software and multiple capabilities to handle different kind of service functions, right? So we need to have a proper management interface, Mano interface between the NFVI part of it and the Mano layers, right? So that you are aware of the platform capabilities, and based on that, you'll be able to do the workload placement or be able to monitor what's going on in the platform. And of course, for that, important part is the data models as well. So these are some of the effort is happening in Etsy. Some of them is happening in the different open source projects. Example is OPNFV, and I gave you an example of the barometer project. And the other one is the Mano. That's also happening in multiple different forums. So I won't go into details on all of this, but I'll just touch upon some of the challenges in the virtual interfaces, right? So you can have multiple different kind of vSwitches, right? So one of them is the stock vSwitch, is a kernel-based vSwitch that's already available. OVS is an example, but there could be other. Linux Bridge is another example. There could be multiple different variations of that. But on the right-hand side, I'm also showing you options where you have a DPDK-based vSwitch. And if you look at how the VNFs are interfacing with these virtual switches, is using Vertigo is one of the examples of the interface. This is a para-virtualized interface. You're also seeing other emulated interfaces as well. If you are operating in a VMware environment, you might be having a different virtual interface that they are providing. And similarly, in Microsoft, you might be seeing other interfaces as well. So the key point here is there should be a consistent interface, or the VNF needs to be capable of providing capability to work across these multiple different interfaces. And when you're talking on the right-hand side, I'm showing an SRIOV NIC. The example which you asked is what if the VNF directly interface with the hardware? And in this case, you have multiple different vendors, and then there is a variations on what kind of virtual functions are supported there, and how do we ensure that there is consistency there? So you get the same level of capabilities when you're operating across multiple different underlying hardware in a platform. So that's another challenge, and the industry is evolving to solve some of these problems. Ideally, we would like to have a model where you have an abstracted API at the platform at the NFVI level, so that you have a vSwitch that's able to run in software, or able to take advantage of some of the services that are offered in the underlying platform. It's possible that the underlying platform is much more intelligent and capable of handling some of these advanced packet headers that I talked about, in which case the virtual switch might be able to take advantage of the capabilities, acceleration capabilities provided by the platform. But at the application level, at the vSwitch level, you want to make sure that it's abstracted, so that if the platform provides that capability, it takes advantage of that one. But if it doesn't provide the capability, then in that case, it can run in software. Same thing when it goes to the application level. In the VNF level, the application, you need to have an abstracted API so that the application can take advantage of underlying capabilities that are available in the hardware to provide the acceleration. So that's where we wanted to be in the long term. But in the short term, I think we are trying to solve some of these problems, whereby at every layer, right? So underlying, we want to be able to have a consistent API at different levels. One at the NFVI level, at the same time the interface between the NFVI and the next higher layer at the application level. So with that, I conclude my presentation, and then I'll open up for questions. And
probably a dumb question. So my understanding is that VNF and NFVs are primarily for the service provider environment. So you have not actually brought that up at all in your talk. So I'm wondering if you have expanded the scope on that.
That's not necessarily true, right? So the concept, maybe the names might be different, right? But then the concept is the same. So as I mentioned, you still wanted to have a service like in a virtual service that's offered in a service provider kind of environment, whereas the applications might be different, right? In a service provider environment, maybe you are running a provider edge router as a VNF, right? Whereas you come to a public cloud data center, you might want to bring in firewall capability. It's a virtual firewall that's running as a VNF in the data center, right? You may not call it as a VNF, but it's still a VNF, right? You may not call it as a network function, but it's still a network function, a virtual network function that's running in that environment. The same thing is applicable to an enterprise as well, because enterprise is kind of a little bit behind to adopt this technology. But if you had been to the recent Open Networking Summit, you would have seen some of the enterprises came and talked about how they are adopting this technology and then bringing in. They are seeing the public cloud and they are seeing the service provider kind of environment, and they want to bring in the same level of capability in the enterprise as well. And you would see, in their remote offices and branch offices, you might see them deploying, virtual CPE instead of getting a physical box, right? So that's the model that's coming up in the enterprise as well. So it's not necessarily tied to a service provider environment. So this NFV and the concept is equally applicable to multiple market segments.
Okay, another quick follow-on dumb question. So VNFs, what is the actual realization of that? I mean, what is it? Is it a VM or?
Yes. So today it's a VNF, and you can also containers is the future, or you would see that some of the VNF vendors might be talking about both VNF available as a VM or it could be as a container, but both you can see, right?
I mean, your talk is quite a high level, but I'm just curious why there are no NFV and SDN unicorn. If you look at the storage and computer space, there are quite a few like Nutanix, and why there are no unicorn in this space? SDN and NFV. You will be seeing, one of the challenges here is like you're having, the NFV infrastructure provided by a different, provider or a vendor, or yes. The Perm got acquired by VMware for only like 20 million, and its total funding like 35 million. So it's quite a huge loss, So I'm just curious why this sector obviously is very hot, but it looks like not on the track, As I'm asking.
So when software-defined networking startup. It's close to unicorn. So not 1 billion, but it's kind of close to that. So
I will step back and talk about the consolidation might happen in the industry, but the key point here is when you are having a lot of open source projects, right? When you want to bring in the whole system together, the whole platform together, which includes the VNFs, it includes the hardware platform, includes the software and the management, everything together. We are talking about system integrator, right? Who can bring in all these services together, right? So in a service provider kind of environment, in a service provider and some of the, I would call it as the OEMs are equivalent of, TEMS, you can call it as, they would be gearing up to provide these services together. Some of them might, transform to being a system integrator that will be able to integrate all these services together, right? It may be that for a certain solution, it may be that open source is a good model, but in certain other cases, you might have open source paired with other commercial solutions together, right? In order to bring that.
Please use the mic.
So
Can you please repeat?
Yeah, so there are no opportunity for startups because like a bigger brothers like Intel, Cisco, Juniper, they are so aggressive. There's very few rooms for startups Is that a reason?
I wouldn't say that. There are companies that are innovating. I mean, there's space for, a lot of companies to innovate in this area, right? It could be in the VNF space. There's a lot of innovation can happen in that area. You can see smaller players to larger players who are bringing in, VNF, right? Different kind of network functions. And then you're also seeing that same thing in the NFVI layer, right? So there are open source models and there are commercial solutions available. Same thing, management is another area which is an open, where you can have a lot of innovation happening in the management area. There are open source projects as well, and you also will have, other, private providers or commercial offerings as well in that area, right?
Related question earlier, as you show the various models and multiple flavors of VNFs and sandwiching different kind of implementations, one question I have is what specific areas that you have come across which have advanced the inter-service transfer of the packets to be faster and efficient, be it on the same CPU or maybe on the same CPU, because typically these functions are written independently on isolation, but if you want to get performance, you need to co-locate them in the same CPU, same cache, and all those things. So how is that? Have you seen played out anything that is coming or emerging that helps to make this boundaries much smaller for it to better performance? I don't know if the question is clear, but my goal is more like a lot of these functions, the gateway and the VPN functions, if you put them in the same CPU, is there any automatic enhancement that are available that you can say that they're all on the same CPU, don't go and copy it over and send it over again and come back in another interface, virtual or not?
So that's a good question. So today, it's more evolving, I would say, right? So one of the points, maybe I'll start with the first question, saying that, okay, what kind of capabilities are available for inter-VM, communication, be it, VM to VM for, between business applications, or VM to VM across between these network functions, right? So the challenge there is in software, right? So once you have a software that's also doing this inter-VM communication, the same software is also forwarding traffic between the network as well. And so you'll be limited by the packet processing capability of the virtual switch. Of course, the newer platforms are evolving, and it's able to handle a lot more packet processing. And at the same time, we're also having accelerated, vSwitches, software accelerated vSwitches like DPDK OVS, and VPP is another example that's able to provide a lot more packet processing capability that can allow you efficient, VM to VM transfer. Some of the customers are also looking at, this is not good enough for me. I wanted to have hardware-based capabilities, and they are using examples SRIV-based NICs in order to do that, the switching. So they are able to get better packet processing capability by eliminating some of the bottlenecks that are available in the vSwitch, but it comes with its own cost, right? There are limitations in terms of, VM migration and so on, right? So those are the challenges. As we move forward, we need to look at capabilities where, better network controllers, if you want to do better VM to VM switching, that also handles not just simple switching, but able to understand some of the higher levels in the packet, right? So they can peel through the onion and be able to handle the packet processing better. That's one example. The other thing is the software also is, becoming better and better to take advantage of, doing the switching, much better. But in the future, you would see that the platform providers will also be able to provide better, VM communication in the platform itself.
Okay. The reason I ask is because you had mentioned TLS offload and decrypt also, right? Encrypt, decrypt, offload. You are doing some portions in the software, you have to send it back to the hardware, again bring it back, and again do some other things.
So that's a very good point, right? So I think that was the second part of your first question is how do I know that the underlying platform has these capabilities so that I can go and do the intelligent workload placement? This is where exposing the platform capabilities through the Mano layers, that's kind of important, right? So if you're following OpenStack, we have been working on enhanced platform awareness. How do we bring in the platform capabilities, expose the platform capabilities all the way to the orchestration, so the orchestration knows that underlying platform has crypto acceleration capability. Our underlying platform has a special, network NIC so that it can handle this, or the platform has, certain class of, CPU, which has, newer generation of CPUs that I want to launch this into this kind of a platform, right? So now once the orchestration is aware of all these capabilities, then you can do an intelligent workload placement. That's number one. The second thing is I talked about the API in the last part, the ideal end state, where you have an DPDK-based API which also is aware of the underlying accelerator. So in which case, the platform capabilities, that the underlying platform is capable of that, in which case it will take advantage of that. But if the same software is running in a different platform, knows that, okay, the underlying hardware doesn't have the capability, I want to use the x86 instructions in order to get the same capability. Maybe it will be running at a lower performance in terms of packet throughput, but it will still run, right? Ideally, you would like to have the VNF portable in the sense that it will be able to run anywhere, anytime, right, at a different scale.
Thank you.
I have a question regarding the Mano. So in order to achieve this service chaining, what is the minimum complexity, or how many orchestrator we really need in the Mano? There is NFI orchestrator, there is a SDN controller, there is a service orchestrator.
That's correct.
So what is is there any optimal, is one box solution, or as of today?
There's no, one box solution. If you look at OpenStack, you can see that multiple different projects within that OpenStack which ties it together, right? You have, which ties all of these services together. The same way, if you look at, a little bit on the other side, I think maybe to answer your question, there are some solutions available today, but then this is the problem that we need to solve going forward as an industry, right? Yeah, that's what I would say. Like today, how the service providers are bringing in this is like, it's not that the solution is available where you have a seamless, solution which understands the platform capabilities and understands that you have, service chaining running in there, or it understands that the underlying platform has crypto capability and so on. It's there, it's happening. I'm not saying it's not there, but the system integrators are bringing in the solution together. But if you are looking at a readily available solution that, with finer knobs, that's evolving. I think industry is working together on this area.
As of today, like different vendors are there,
yes,
competing in the SDN controller space and the service architecture space. I don't know. So that's why the optimization maybe happen, but that's what I'm looking for at least.
I think in the interest of time, we have the idea relay active.
Okay.
If Illango can stay back, please, ask him questions.
Because I'll still be here for a few more minutes, so we can have offline conversation as well. And thank you very much for being here and listening to